So, next we will see what are the different types of combustors that are being used or have been used in gas turbine engines. So, this is about the types of combustors that we encounter. Okay. So, there are essentially three types of combustor. First is this can type combustor, where we will see the combustor essentially looks like a can, and these cans are essentially circumferentially arranged around the central shaft. Okay. Of course, you see that the if you look into the basic architecture of the gas turbine engine. Okay. So, this is the cut section. So, you see the combustor has to occupy this annular space which is surrounding the central shaft. So, the overall architecture of the combustor has to be in an annular form. Okay. Now, this essentially this we are just showing this three. Here we are just showing only three this cans, but actually it looks something like this. Okay. That this is arranged in this form of beads around the central shaft, and this is how the can type combustor looks like. So, these are the central injectors that are being shown, but here each of the combustors are essentially separate. The central part contains the shaft. Okay. So, this combustors are arranged in this manner. In the can annular manner, so it is similar to the can combustor, but there is also this this shroud surrounding these cans, and there is some airflow that can happen across this different can annular combustors. In the annular combustor, you see that there is this injectors are just placed in this annular space, and there is absolute interaction between all the combustors, all the essentially individual burners, which are where the flame is essentially stabilized like this, and there is nothing that separates or physically separates this flame from each other, and the flame and flow can interact. And what is most modern engines essentially use this type of combustor, whereas this is the most primitive type of combustors. This is the most these combustors are used in the most primitive engines, or the first engines which was set by the Frank Whittle, etc. But modern engines like the Rolls-Royce engines, GE engines are all essentially use this annular type combustors. So, what is the can combustor? This is an example of a can combustor. So, you see that all these combustors are essentially put into different cans, and this combustor has a cylindrical liner inside this. This has a cylindrical liner inside the cylindrical casing. This was the first kind of combustor. Okay. Now, the advantage is that this was very easy to develop, because you just need to develop one can combustor, and then you can replicate that combustors and arrange them in a circumferential manner. So, and it is easy for maintenance also. You can just take out one combustor and then repair whatever has been done, and so that is how this thing can be done. But of course, as you see that the metal that goes into the individual cans, okay, that adds excessive weight and size that makes it unsuitable for aero applications. In anything related to aerospace applications, weight is a very important factor. So, you want to have minimal weight for the engine. Okay. Now, the second thing is the can annular combustor. So, here you see that in addition there is this outer casing which is provided, and also these are provided in this annular space, and this can combustor essentially is sitting in the annular space, and then there is this flame tube where essentially the flame can pass from one combustor to the other combustor, and you can have only essentially one igniter. The idea is that you can have one igniter, and then the flame can basically interact from one combustor to the other combustor. So, ignition, if it is ignited, a kernel that is ignited in one combustor can develop into a full flame, and then that full flame can send out the hot gases to these flame tubes, and those can ignite the other neighboring combustors, and so on and so forth. The whole all the combustor in the engine gets ignited. Okay. So, this was also a little bit used in old engines, and then once again the chamber design is not difficult, and working pressure can be higher than the can combustor, because here you have two layers of protection. Okay. The main disadvantages are that these crossfire tubes are very notoriously difficult to develop, and achieving reliable and air sustainable flow pattern is also very difficult to achieve. Okay. So, that is a very difficult thing, that to ensure this flow through these narrow tubes into and in and out of these different combustors are not very simple to achieve, and that led to this abandoning of this kind this annular combustor. This is this Rolls-Royce engine, this what you see here, and Rolls-Royce combustor that you see here. So the annular liner is here. The thing is that individually these are the injectors. So the combustor is essentially occupying this space. Okay, so this is the space of the combustor, and then this essentially has a goes a full along this occupies this full annulus between the compressor blades and these turbine blades. So the compressor blades are here and the turbine blades are here. So in between this annulus and this is the hole for the shaft. So the shaft will be something like this. Okay, so in between these this combustors occupies this space, and it's a full annulus design, and where individual injectors are not physically separated. Okay, there is absolutely nothing that separates them, and it's just an annular liner is placed concentrically inside the annular casing. So this is the popular combustor that is present in most ultra modern engines, and the advantage is that the clean aerodynamic design makes it more compact. Okay, so because there is no separation as such and there is no walls intermediate, then this as there is this combustor can allow can have much less can occupy much less space, and it also has much less weight because it has totally done away with the cans. Okay, now also the pressure loss is also very small because you do not have much interaction with this kind of these walls, and we can aerodynamically, more importantly, we can design this flow path in a much better way. Okay, the disadvantage is that because there is less metal, of course there is less material to take the buckling load. So the buckling, this outer liner takes a huge amount of a buckling load, and this high cost of air supply air required for testing. So it's very difficult to, I mean, though people do, that's like this combustors has to develop systematically from one injector to the multiple injectors to the full annular testing. So development is more difficult and more challenging than a of course a single can type combustor. Okay, so this is how this. So we will talk about more about this annular combustor. So this is a section view of a CF 650 annular combustor from General Electric. So as you see that that this is of course much more complicated design than this diffuser combustor nozzle that we had shown you previously. So of course here you see that what we have is here is the diffuser, where the flow comes in from the compressor. Okay, so the flow is flow entering flow from compressor enters into this and then it passes to this diffuser, where as you see the cross section area increases. Okay, so this is bigger, and then the flow essentially slows down through this as it passes through this thing. Of course you should here the area is not exaggerated, but you see it's a full annulus, so the actual area increase is actually quite large than what is seen in this what can be understood from this this picture. So the air comes in here, and now it can essentially, as you see that here you have the injector. Okay, so but before that the air essentially can get split into these two parts. So it can come through here, and it can also, so this is only the central section, so there is ample space for the air to essentially enter into this region also, and then it essentially enters into this essentially recirculates and enters into this thing, and passes through this swirlers on which the injector, this atom injector is mounted. So this injector essentially sends out a liquid sheet like this, which essentially breaks up, and okay, it's not so big. Let's draw it a little more accurately. So this this injector sends out a liquid sheet, and of course in a swirling environment. So this whole flow is swirling like this. Okay, and then the as it evaporates, so a flame will be formed. Okay, a flame like this can be formed as the droplets, the liquid droplets that is injected from here. So, if I draw this fuel path through this, it comes in here, it comes in here, and then it goes in and this forms the spray. Okay. But these swirlers, these are the swirlers which essentially swirls the flow, okay, and the flow is essentially swirls, and at the same time it also creates as the swirl numbers are selected, you will see that the swirl number here is essentially the ratio of the axial flux of the tangential momentum to the axial flux of axial momentum. So, it's essentially creates provides a tangential momentum or a rotational motion to the otherwise straight flow. These swirlers, and then these when that exceed a certain number, when this tangential momentum is high enough, tangential momentum that has been imparted onto the flow is high enough, then there is a phenomenon called vortex breakdown when there is a flow recirculates. So, you see this kind of flow recirculation, and then that helps in essentially stabilizing the flame. Okay, so here you see this flame being stabilized like this, and then there is also this air which is coming from here. So, this air is at a very this flame is at a very high temperature, which we do not want, as you remember, which we do not want this kind of a high temperature air. So, then this air comes in later through these cooling holes, and it reduces the temperature from here, essentially T reduces, so that at this exit your temperature is the turbine entry temperature. Okay. So, these are the different parts, the diffuser, then you have this the injector, the igniter, this is the casing, and this is the liner. So, the liner is essentially the boundary between the this main primary combustion region to the outside casing of the combustor. And then this is the inner liner, which is the central part, and of course, this is a full you have to see that the axis of symmetry will be somewhere here. So, it is essentially a full circumference, it is like this. Okay. So, that what one needs to understand. So, it is just a small cut section of this annular combustor that we are showing here. We will talk a little bit about this in the coming slides. So, as you see that one of the important parts, so this is the diffuser. So, even though this is a combustion class, we will just because it is an important part of the combustor, we will just tell you what the diffuser does. As we have seen that the diffusers are used to reduce the compressor outlet velocity and recover the dynamic pressure. Okay. So, the main purpose is to reduce the outlet velocity. So, so that the pressure loss is less, and also in doing that it recovers some of the dynamic pressure, and the combustor pressure loss can be thought about as that is the 3 is the combustor entry point and 4 is the combustor exit and the turbine entry point. So, it can be thought of as having two parts. The loss emerges from two parts. Number one is the cold loss and the hot loss. The cold loss is that because you are pushing in the air, to push in the air you need to have some kind of a pressure drop, okay, because there are viscous losses on the walls. So, to maintain the constant velocity, it is like a pipe flow, that if you want to maintain a constant velocity profile in a fully developed pipe flow, you need to have a constant pressure gradient, okay, so that the viscous losses can be, so that the fluid can overcome the viscous losses in the walls. So, so that for that there is a cold loss, always inevitable cold loss, and then there is a hot loss, and this cold losses corresponds to the diffuser and the liner pressure drop. Now, in the liner pressure, when there is this drop, essentially also when there is a this, because of the tortuous path it follows to the liner because of the essential cooling holes, etc. It actually creates some turbulence which helps in mixing. So, this loss is cold loss is not so bad, but in the diffuser, of course, diffuser also, because of the walls, it has some losses. So, now the P hot is that when you add heat into a flowing gas, which is, if it is a subsonic gas, then of course then there is a pressure loss as we have seen, but and this pressure loss is directly proportional to the U square, which we have done this, if you remember, in the governing equations and the premixed 1D premixed flame class. Okay. So, this is about 0.5 times rho u square times T4 by T3 minus 1. So, with this we can calculate the pressure loss, and to basically reduce this pressure loss, we wanted to have a low u, So the diffuser actually is used for that purpose. So and also it ensures that the liner gets smooth and stable flow. So the diffuser has multiple purposes in that it not only recovers, not only minimizes the pressure loss, but it also ensures that the flow which can be strongly turbulent coming out of the compressor, that passes into a very aerodynamic manner into the combustor. And there are two kinds of diffusers essentially. Then one is a fair diffuser or an aerodynamic diffuser, which essentially divides, this is the aerodynamic diffuser, which divides the flow towards the annular and the annular zone and the combustion dome. So the annular zone is essentially this. So you see the diffuser essentially guides the flow into the combustor. So but the flow can go either in this manner, or it can go into the main dome, combustion dome region. So how this will happen, how much flow will go into the center, into the combustion dome region, and how much combustor will go into the outside cooling region, is completely governed by the diffuser. So this diffuser is a very designing the diffuser is a very important task, because see, if you have more air going into this outside region and very less air going into this, so then you will produce you will have very fuel rich combustion, and that will produce all sorts of pollutants. Okay, so you don't want that. On the other hand, if there is too much air going into this central region and very little air going into the cooling region, then your cooling will not be effective and the temperature profile will be bad, and also you don't your combustion may be outside the stability margins. So this diffuser, there is no way to essentially tell the flow that you go this path, you go this path. So all you can do is to guide you design the diffuser in a manner so that this flow gets divided into the proportion that the combustion designer wants. Okay, so the equivalence ratio that will be here will be essentially governed by how the diffuser is segregating the flow into the main dome region as well as in the outside region. So that is why the diffuser plays a very important role. And you see there are two diffusers, this aerodynamic diffuser and dump diffuser, and the dump diffuser lets the flow divide itself into the annular and the dome region. So this dump diffuser essentially creates a sudden expansion into this, as you see here, and of course here you see in the dump diffuser your velocity reduction will be much more than in the aerodynamic diffuser. So depending on the situation, one can use a dump diffuser or an aerodynamic diffuser. Okay, so there both variants are actually seen in the modern engines. Okay, so next let us go into the combustion chamber itself. Okay, so the combustion chamber, as you have seen that this is a schematic which is essentially the schematic of this part. Okay, so so the combustion chamber essentially you see the flow coming from the diffuser here comes into which gets divided into the outside this cooling flow and the main flow that goes into the dome. Okay, so you see that here at the center you have the fuel nozzle, the fuel will be coming from here and gets injected. Okay, so let's so the fuel will be coming and getting injected from here, and it will form this spray, and then the air which is coming from here, okay, will pass to the swirlers, and it will develop this swirling flow and it will recirculate. Okay, it will recirculate here, and then as this recirculates and meets this this spray, it will essentially form it will mix, and then once you have the igniter, it will create the flame. So the primary zone, here you have the most of the flame inside this primary zone. Okay, like this, and this is the most important region of the combustor, because this houses your essentially converts all the chemical energy to this to the thermal energy by the process of combustion, which we have learned so far, and it's a very complex process that happens here. So you have got essentially the processes. If you just summarize, you have got the liquid has to atomization. Okay, then you have that atomization means the breakup of the liquid sheet into small droplets. Okay, there can be primary atomization, secondary atomization, and so on, and then this must fuel these small droplets big droplets goes into small droplets. So then these small droplets must evaporate. Okay, so this evaporate to from this mix to form this and then it must mix mix it must mix with fuel air mixing. Okay, so you have got to have fuel air mixing, and then you have to have this then you can have the combustion. Okay, and depending on the fuel air mixing, you can have some places you can have most non-premix combustion, you can have premix combustion. As you see that in the modern engines, people are trying to go have a pilot non-premix flame and a premixed main flame, so you can have both. But of course these are all happens in a very strongly turbulent flow. Okay, so and individually, so the flame will not be not a smooth and a nice flame like this. So the flame will be strongly wrinkled and a strongly turbulent flame when you look at it instantaneously. Okay, so individually you can look into this flame and you can find all the things that we have studied. All the things are essentially present. It involves kinetics, it involves oxidation mechanisms, it involves, you need to know this whole process of this fuel air mixing and how it happens is governed through the governing equations. And then you have to have then individually, if it is a non-premix flame, then locally you can use this this flamelet approximation that you have seen, which involves this the solution from the chambered flame. And then if it is a premix flame, 1D premix, if it is a turbulent premix flame, some place you can use this analysis of the 1D premix flame that you have seen and apply the stretch concepts to derive a more generalized function of flame speed. And you can use, if it is a premix flame, you can use the G equation to basically find out how it will evolve. And of course it involves limit phenomena also, because that limit phenomenon will govern you how, in what margins it will be stabilized, or it will be in where you can ignite it and where it can extinguish. So all these things essentially feed into this small combustor of a gas turbine engine that you see. So all the things you have learnt is very relevant and feeds into this. So if you want to simulate this process, you need to know all these things. So that is why this course is we have designed this course in that manner. Okay, now this is the primary zone, and then we go into this into the secondary zone, where you have secondary holes and you have some coolings like this, and from this cooling which reduces the temperature to some extent. And then finally you have the dilution zone, where you feed in a lot of air, and then this dilution zone will essentially control the temperature profile that comes into this. So finally you need a temperature profile in some manner which is governed by the stress situation in the turbine. So this cooling hole once again controls the will control this temperature distribution, and that will ensure long life of the turbine blades. So this intermediate, so the primary zone is where the main combustion takes place, and the intermediate zone increases the combustion efficiency, it reduces the pollution we will see how, and this dilution zone essentially creates the required temperature profile for the turbine inlet. So these are the different processes that must happen. So as you see that, just to recap, the primary zone essentially is used for anchoring the flame and to provide essentially the sufficient time for achieving the total combustion of the incoming air fuel mixture. Okay, so the primary zone is designed, so that is why you have solar, so that the fuel air mixture have sufficient residence time. If it was just straight flow coming out of the diffuser, this diffuser flow can be of the order of 50-60 meters per second. Okay, so if that flow, you cannot stabilize the turbulent flame as is, so you need to have some kind of a flame stabilizer. So the turbulent so the primary zone essentially houses this injector and the solar. So the injector is essentially mounted on this solars, and it provides this kind of a recirculating flow. As you see, the spiral flow essentially ensures that the flow has sufficient residence time in the primary zone, where you can have complete combustion of incoming fuel air mixture. So it creates a toroidal flow reversal that entrains and recirculates part of the hot combustion product. So that is the second thing it does. So once you have a flame stabilized here, Okay, once you have a flame stabilize this and then you have recirculation, so the fuel air mixture comes into here, then it recirculates and then it comes back again. So when this comes back again, it is in touch with the fresh mixtures, and this hot products essentially can serve as an ignition source. It can transfer the thermal energy by conduction convection processes into the fresh mixture, and that can help in achieving continuous ignition. And this toroidal flow can be created with a proper swirler, baffle or a bluff body. But typically in aero gas turbine engines, swirlers are used, whereas bluff bodies are used in afterburners, which we will take up in a later. So strong and stable primary zone airflow can provide wide stability limits, good ignition performance and reduce combustion noise and instability. So the design of the primary zone is of extreme importance, okay, and it's this part, understanding this part and simulating this part is of extremely high importance, and is basically the most important job of a combustion design of a combustion engineer in working in an aero gas turbine engine. So here we will take up little bit about swirling flows because as you see, all gas turbine, modern aero gas turbine engines use flames in use essentially flames in swirling flows. So this is how the swirling flame looks like, and this is how and actually this is a laboratory experiment, but this is how actually the flame inside but annular combustor would look like, though this is a very laboratory experiment, and this is essentially the flame in a strongly swirling flow. And so these are all essentially laboratory experiments, but these are essentially different variations of the flames in swirling flows. This is a simulation that you see here. It is a largely simulation of swirling flame, okay, and this is this, as I said, is a multiple swirling flames arranged in an annular combustor. So this chamber comprises of 16 injectors and is equipped with a quartz cylindrical valve for doing optical diagnostics. So we will talk about optical diagnostics in the later class when we will take up flame stabilization in an afterburner. But this is how essentially the back plane of a gas turbine combustor look like. Okay, so looks like, and then the flow comes in, as you see, it passes through the swirlers, and you see that this develops this it develops this swirling pattern into this thing. So as I said, that the swirl number is an important parameter, and it is characterized by the essentially the axial flux of azimuthal momentum to the axial flux of axial momentum, and it is governed by this generalized expression. Okay, so so the thing is that as I said that when the swirl number is about in a swirlers which does not have a center body or a very small center body, and the flow is fully developed and is fully swirling. So in those cases, if the swirl number is greater than about 0.6, then there is a phenomena called vortex breakdown. And the reason is can be it's a complicated fluid mechanical phenomena, but if you write down the Navier-Stokes equation, it essentially comes down to u theta square by r is scales as dou p dou r. Okay, so when u theta square by r is large, then there is a this dou p dou r, then there is a pressure gradient, inward pressure gradient that develops, and essentially it is like a balance of centrifugal force with the acceleration, so then this dou p dou r essentially causes the flow to recirculate. Okay, so that causes the vortex breakdown, but this vortex breakdown phenomena is very important for gas turbine engines because it ensures stable combustion, and this continuous toroidal recirculation zone helps in continuous circulation of the products. So that is a very important thing for a gas turbine engine. So what does the intermediate zone do? The intermediate zone, which follows the primary zone, is at high temperatures the primary zone dissociation reactions are favored. Okay, so which we have learned from the chemical equilibrium class, that causes this dissociation essentially causes the shifting of the temperature peak from the stoichiometric side to the slightly to the essentially to the rich side. Okay, so and that is due to dissociation, and the sudden change in temperature at the dilution zone makes all the reactions frozen actually. So because there is some cooling air coming in, it immediately reduces the temperature, so the reaction zone gets frozen. So the exhaust gas contains essentially high amount of CO and H2, and what this the intermediate zone essentially provides you enough air in the combustion chamber to decrease the temperature and burn the CO and H2. Okay. So, that is the thing, that is if this intermediate zone was directly followed by the dilution zone, the dilution zone puts in lot of fuel, lot of air, right. So, that would have cooled this temperature to so that would have cooled the high temperature combustion products to so low temperature values that the reaction will be frozen, and that at that point like if it was kind of a situation of chemical equilibrium, then that will contain lot of CO and H2. So, you need to provide a little bit more air in the dilution in the intermediate zone, so that you essentially can burn up the CO and H2, and if unburned hydrocarbon or soot any, and this can be used for to reduce the temperature slightly, but not as much, so that the situation is conducive for the combustion of the carbon monoxide, hydrogen, unburned hydrocarbons and soot, okay, and oxidation of the soot. So, this is what the purpose of the dilution zone is. It essentially acts as a pollutant controller, okay. And with increase in the pressure ratio around 1970, intermediate zones becomes extinct, but stricter emission rules are making it relevant in a combustor, okay. So, this is the intermediate zone's role to essentially reduce the carbon monoxide and hydrogen. And the dilution zone essentially, as you see here, that there is a lot of dilution. Here is a breakup of the total air inside the combustor, okay. So, you see that about 80% of the air is going out, and only the whole about only 12% of the air is actually used for direct combustion in the primary zone, whereas this out of the 80% air that goes out, 20% enters into the primary zone, and then there is a lot that slowly enters into the dilution, and there is about the remaining 60% of the air essentially comes into the dilution zone, okay. So, this of course this does not have a intermediate zone. So, you see a bulk of the air is actually used for dilution, that is reducing the temperature of the combustion products to acceptable levels for the turbine entry temperature. So, this is the purpose of the dilution zone, that the exhaust that get out of the combustor at combustor is given a specific temperature profile before it enters into the turbine, okay. So, this profile is known as the pattern factor, and the dilution zone is made to achieve the pattern factor. So, this is controlled, the aerodynamics is controlled in such a manner, so that the exit temperature profile exactly matches that is required by the, or it is desired to match that that is required most conducive for the turbine. And as you see, about 60% of the total air is used in this one. So, of the so a lot of air, you see that there is aerodynamics in this combustors is very important, because it leads to the cooling and control of pollutants, and also for achieving the particular pattern factor. So, this is the purpose of the dilution zone. So, in the next part of the class, we will take up how we basically inject fuel, and what are the processes which basically breaks up the fuel into small droplets, and how to basically inject the fuel inside this combustor, which is also a very important topic in gas turbine combustion. So, see you then.